Can you see my screen?
No.
No.
See you.
That doesn't work.
A screen button at the bottom.
Okay.
No,
You
it's
see
going.
it
No, it's going.
Now
Okay.
we see.
So, Balaji, should I start, Sab?
Yeah, go ahead. Who are
All
these
right.
people?
So, Sab tells me everybody knows Balaji, and that's most likely true because let's say he stuck up above all of us while we were in IIT. You couldn't miss him walking around. And but even though he was a year senior to us, we had the pleasure of interacting with Balaji all through our IIT case day. He took mercy on us by not playing sports like basketball and volleyball, and he led it to the lesser mortals. He didn't take advantage of us with his height. But he taught us many things. Like my love for cryptic puzzles stems from Balaji teaching me how to do them. But anyway, enough about the IIT stuff. Since then, he after IIT getting his degree, master's in physics, he went to the Ohio State University and got his PhD there. Then I kind of lost track of him, but I think he spent some time in Paris and then Canada and God knows some more countries maybe in between. But for the last 25 or so years, headed up he basically headed up the Princeton NOAA facility for uh, climate modeling or fluid mechanical geophysics study. I forget what the exact title of that institute is, but something similar to that. And his contributions, I mean, I at his retirement from there last year, they had this thing called the Balaji Fest. And it was a tour de force on his massive contributions to climate modeling and the worldwide interactions and synergistic things he set up during his career that it was just jaw-dropping in the amount he achieved there. So Balaji, really kudos to you. But since then, of course, he's learned how to do more boondoggling. He has joined the Schmidt Futures venture as senior scientist, I believe. And from there, I think he's on a perma boondoggle trip. This one, I show you a picture of him with, as he said, several primates, his wife, his daughter, and the great ape at the back. But in all seriousness, his recognition of being a top-notch climate scientist is not just recognized by folks in the US, but internationally. And one of the things that I was always impressed was with when Trump came into power at the US, he started poo-pooing climate change, etc. And that's when Macron swept in and said, instead of making America great again, why not make the planet great again? And he attracted 25 top US climate scientists to come to France and all expenses paid and live there basically for 5 years. And of course, our friend Balaji was one of them, clearly among the top 25, but I think he was one of the first chosen to do that. And he, not only because of his height, but his stature, moves around in different circles, clearly with Macron, the late John Lewis, who, of course, some of us are big fans of, and once in a while, he comes to lower stature. And, if you're in Paris, you get to visit Balaji and meet him. Of course, Balaji is currently somewhere in the heart of Africa. I don't know if I can reveal it's Rwanda, but I just did. So Balaji, I forget the title of the talk, but over to you. And looking forward to learning even more than what I learned at Balaji Fest. So all yours.
Okay, you may have to unshare so I can share.
Okay, that's going to be a challenge again, but let's see. What the hell?
Okay, thanks, Sanjay. Anyway, while you're, let me thank Sanjay while he's fiddling with some knobs there for this generous introduction. It's been great fun, and we have stayed in touch with some of my IIT buddies over the years. I did stay in physics. I got my degree. I don't know if you remember, most of you. I was not an engineer. I was a MSc physics major, and I kind of more or less stayed in that until, as Sanjay says, I started boondoggling last year. So right now I am in Kigali. That's where that ape picture is from. 3 days ago, I visited Volcanoes National Park, where you can have close encounters with gorillas. I went to another national park also where we met chimpanzees. I'm going to start with an apology. I mean, I'm here with a small work computer, and I did not. I had prepared a slide deck for this, and and this is my dog ate my homework prologue. I did not upload those to my work computer, so I'm going to give you a slightly older version of the same talk. But still, I think we'll cover these issues. So it's advertised in Khusraw's email as a talk about climate change. We'll definitely talk about climate change, but this is mostly about climate modeling, and links with computing will come across. So I know that Gopal gave the last talk where we was talking about with semiconductors, where they're going and so forth. So some of that history has paralleled the history of climate modeling. In fact, to go back, let me start with a share screen first. Let me make sure that I know how to do that. So can you see this?
Yep.
Okay, there are no black bars or anything like that. Okay, that's fine. So I'll talk about climate models, how they started, and, why should we, I mean, most of our knowledge about climate, of course, there's a lot of observations, but we're talking about the future of the climate change, and how it's going to change in the next decades. So most of that work obviously is done by simulation and modeling. So I'll get into the history of why this lab, this geophysical fluid dynamics lab, why it was in Princeton. So von Neumann basically invented the modern digital computer, based on Turing's ideas at the Institute for Advanced Study. So ENIAC was the first machine he built that could practically be programmed. That was around 1949. That was in Princeton. The
Hey,
actual
Balaji,
machine.
we are only seeing your introductory slide.
Yeah, I'm still on the introductory slide. I'm just chatting at this
Sorry.
point. Yeah. And by the way, feel free to interrupt as Nitash just did. So ask all the questions while we're going. I don't only have 36 slides, not 136. So we can take questions along the way. I'm just giving you the history of climate modeling very briefly. So von Neumann worked at the Institute for Advanced Study in 49, starting in 40. He came over after the war, basically. And then he said, okay, we can use this computer for doing numerical calculations, basically solving PDEs, partial differential equations. The first practical application of that was actually trying to run a weather simulation. So the history of weather simulation was that the equations were discovered by a guy called Bjerknes at the turn of the century. It's basically a Navier-Stokes equations on a sphere. But they're nonlinear, and the Navier-Stokes equations. Any of you who's taken, ESC 221, was it? Was that thermo? One of them was fluid mechanics. Maybe 321 was fluid. These are complex equations. They're nonlinear and they're not easy to solve. You have to make a lot of assumptions. And he basically found they did not know numerical methods in 1905. They did not know how to solve these numerically. There's a lot of issues about stability of discretized equations, which they were not aware of. So he failed to solve the equations. So they said, okay, he gave up the problem of trying to do weather forecasting from first principles. So they went back to the old way that meteorologists do, which is to make maps and all that. So 40 years later, this digital computer is invented by von Neumann. And he says, why don't we now we now can solve numerical equations. So the first calculation was 1950, was done in this lab, geophysical fluid dynamics lab, by a guy called Charney, Jules Charney, one of the giants of the field. And so that's actually, so we can trace our history basically back to the history of computing itself. And then von Neumann also said there's other interesting things. He said, instead of doing forecast, supposing you build a forecast model and you keep running it, he called it the infinite forecast. He said, what would that look like? What would the statistics of weather look like over the long term? So that was an interesting question. Nobody had really thought about climate as a solvable problem until that question was posed. So let's go into what is climate. So climate is what you expect, weather is what you get, is what people say. So weather is what actually happens. What you actually experience is weather. But you kind of expect that if in summer it's going to be warm, winter it's going to be cool. If you're in India, you expect rain in a certain season. So that's the expectation is what is climate. It's the recurring patterns. But expectations keep changing. So NOAA publishes the average weather of the last 30 years. They call it that's the recent history. So that keeps changing as well, because especially in recent decades, what you actually perceive is the difference between weather and climate. Okay, that's what you actually perceive. So if you experience a day which is 20 degrees Celsius, and you're living in North America, if you're living in where I live, which is New York City, and it's December, you will say 20 degrees is a warm day. The same weather, exact same weather, if it occurred in July, you will say it's a cool day, because what you're actually perceiving is a difference. You have an expectation and you get something different. So how do you actually get climate? So weather is noise. As far as climate is concerned, all weather is noise. And you're trying to see the signal. And these residuals are very small. So the daily fluctuations of temperature are like, 10 degrees, 20 degrees, in some places much higher even, but let's say it's 10 degrees. We are trying to find a climate signal which is 1 degree or so per century. So it's a very small signal. So you have to build models that are fairly precise so you can remove this noise and find the signal. What makes it complicated also is that it's not a steady state. There's a lot of it fluctuates around some equilibrium states, and those equilibrium states also can shift. It can bounce around. So these systems they're chaotic systems, they can have metastability, which means that they may have more than one stable state. So in some cases, you find them also bouncing. And there's also feedback. So if you start really looking at the system, the initial model I was telling you about that Charney and others built was basically just the atmosphere. It's just solving Navier-Stokes on a sphere for the atmosphere. But then it exchanges with the ocean, it exchanges with the land surface. So, and there's all kinds of timescales involved, all kinds of spatial scales involved. So there's the continent. If you want to look at what's called paleoclimate, which is the history of climate change over millions of years, you need to figure out where the continents were. And then if you look at actually how clouds form, then you're actually looking at condensation of a micron scale dust particle and water condenses on it. So, and these things are happening on very short time scales. So if to solve the climate problem, you basically involve fluid mechanics, radiative transfer, chemistry, biology, anything you can think of is all in there. These models are pretty complicated. So let's take a history of this is observations. This is the history of the temperature of planet Earth. Okay, and how do you measure the temperature in the past is a whole talk in its own right, because these are all proxy measurements. You basically, usually what happens is that you look at isotope ratios of, let's say, 18 oxygen versus 16 oxygen in shells, shells, which are the discarded pieces of mollusks. And depending on when they lived, you can from that ratio, the fractionation between two different atomic weights, you can tell what the temperature must have been. And so there are many such things. Going more recently, you measure the width of tree rings. So trees put on one ring of new bark every year, and the thickness tells you how much it grew, and from that you can infer what temperature it was. Anyway, so if you just
real quick, when you say temperature, where are we measuring it? Is it like close to the surface, or is it like a ensemble average, or what is the temperature that we're talking about?
It's a good question. So it's the presumed global mean surface temperature. So it's surface averaged over the whole globe.
Thanks.
So that's what we're looking at here. But the measurements are very local. From that, you have to infer what the global distribution was. So that's these are some of the hard problems. But let's just first take a look at the history itself, because that itself is something that we should take a look at. Then we can look into what all these things happen. So you start from. So the time scale keeps changing, as you know. So we are starting from 500 million years, but as you get closer and closer to the present, I'm shrinking the time scale here. So around the time the dinosaurs disappeared, which is around 65 million years ago, here's where we were. This is the time of the dinosaurs. So this black line here, you can see my mouse going up and down, right? I think I hope you can. So this zero line is present day. So it's a reference to the 1960 to 1990 average. So let's call it the 20th century temperature. So we were like 14 degrees warmer than today. This is all Celsius temperatures, 14 degrees warmer than today. In fact, there's a spike, a very short incident, which is called PETM, the Paleocene-Eocene thermal maximum, where you're actually like almost 17, 18 degrees above today. And during that time, we have records of cold-blooded animals like crocodiles being found near the poles. We have palm trees near the poles, so we know that the temperature near the poles. We have actual fossil evidence to say that the temperature near the poles was over 10, 15 degrees.
But do we know why that spike?
Yeah, that's we'll get to that. So it's some of the modeling of paleo climates is not that easy, but we don't really know the answer to your question, but we know basically what happens, but I'll get to that. So Shah, you had a question?
Yeah, so when you say the average surface global temperature, that means these mollusks that are looked for the oxygen, the ratios are analyzed all over the world. Is that what you're saying?
No, they're found only in a few places. And from that, you have to infer what the global distribution must have been. So that's what models are needed. You have like a few point measurements, and then from that, you have to try and infer a global field.
Okay, thanks.
Okay. So we're
Yeah.
trying to, you use the models to reconstruct 3D states based on a few assumptions, a few data points. Okay. Then it starts cooling. So around 50 million years ago, it starts cooling. So it's cooling. Then you get into the Pliocene. So this is an interesting era as well. So this is when the two Americas come together. The Isthmus of Panama is formed. So that completely changes the ocean circulation because there was a connection between the Atlantic and Pacific, which is gone. And then you get into the Pleistocene, 1 million years ago. By this time, early hominids are already on the planet. They started around 3 million years ago. And here you see we get into this era which has ice ages. So the temperature fluctuates. It goes up and down with a period initially around 100,000 years, 40,000 years. So there's theories. It all has to base, so you know that the Earth's axis is tilted with respect to the plane of the ecliptic. And if you remember your classical mech, if anybody took it, so these spinning objects which are tilted slightly, they do these things called precessions. So the axis will wobble a little bit. So using you can measure the rates of these wobbles, and then based on that, you can see that the angle of tilt changes from time to time, and that can explain some of these ice age phenomena. Not completely, but you can explain some of the ice age by just looking at orbital mechanics. But basically, the point is, this is an unstable climate. It oscillates a lot. So when it becomes cold, which is down here, these are what we call ice ages. During the ice ages, the polar ice caps come towards the equator. And there has never been a proper, what they call snowball Earth, where they actually meet and it is ice everywhere. That has not really happened, as far as we can tell. It might have happened in the very distant past, but it has not happened recently. When I say recently, I mean in the last few million years, just to get that clear. So even though hominids existed, Homo sapiens actually existed during the ice ages. They were nomadic because they basically had to retreat from the ice. They did not have the means of living inside the ice zones. So when the ice boundary moves towards the equator, they moved with it. So they're nomadic. They follow the water. They follow the ice. Then you get to this point here, the Eemian, where this thing marked the LGM, which is the last glacial maximum, the depth of the previous ice age, which is 20,000 years ago. And then from there, it starts warming. It seems to be following a usual warming cycle. Then it reaches this place, which is called the Holocene optimum, around 10,000 years ago, 11,000, 12,000 years ago. The temperature suddenly became very stable. So it became very, very stable. What that means is that everything became very regular. This is when we really have what we can call a climate, a stable climate. When it becomes regular, what does that mean? That means you can practice agriculture. You know that when the rains came last year, the same time the rains will come next year. You can put up cities. You know what areas are going to flood, what areas are not going to flood. So you know what the course of the river is going to be. So you can see, okay, in the maximum flooding, here's where it is. So we can build a city on the edge of that water. So we always have water. So human settlements and agriculture became possible around here. So it's not an accident. And we have stayed stable for 10,000 years until we reach the Industrial Revolution, and then you see the spike. So this is what we're doing. We reached a stage which was not like the ice ages. We reached what's called the Holocene optimum, and then we are giving it a big kick. So this is why, this is a crisis. I mean, this is anything that we call civilization is possible only with a stable climate.
Your
So if
scale
you
is though, is on that other, so it's kind of misleading in a way.
it's a little misleading, but we don't have such stable periods at all. So yeah, and it's not
Yeah.
very stable. You can let's look at it. This is the next slide is showing you a little bit of this. So this is zooming into just to the last 2,000 years. So you have this thing called these are all various reconstructions. Okay, so the colored lines. So the differences between them, don't worry about it. But basically what you're seeing is there is a more or less a consensus that at least in the mid latitudes, that means where there's Europe and all that, outside the tropics, there was a distinctly warm period around 1,000 years ago, and a distinctly cool period around 500 years ago. So we call it the medieval warm period in the Little Ice Age. Little Ice Age, we have historical records from Europe which talked about Thames River and Rhine River were frozen in July. So we've had incidents like that happen in the past. Once again, if you look at the very edge of this, we are doing a temperature spike at this point. There's nothing like this we have seen. This temperature spike has not been seen for millions of years. So the other thing is that the medieval and Little Ice Age, these two things probably were only regional. We only know about them from European history records. We don't have any records that says that there was a warm and cool period in India, for example. There's no record that says that, because so the tropical climate is different from the mid-latitude climate. So these may be only regional. Right now, there is a global signature. Right now, the current warming that we are seeing, that we are actually measuring in the last 150 years, everywhere, there's no place on Earth which has got cooler relative to 150 years ago. Everywhere it's getting warmer. Okay, this is another thing about the links between CO2 and climate. So I'm talking about mostly what most of the current crisis dates back to Industrial Revolution and the fossil fuel economy. But things like this have happened before. So this is the top line is showing some CO2 parts per million measurements taken from ice cores in Antarctica. So WAIS stands for West Antarctic Ice Sheet. So these are two domes from which you can take a core of ice, and inside the ice there are tiny bubbles, and the ice builds up over time. So depending on how deep you dig, it's giving you a record of past CO2. So you're seeing around 1600, around the time of the Little Ice Age, there is a big dip in CO2. And why did that happen? This big dip in CO2 in parts per million. It can be traced to European arrival in the Americas. Americas had an agricultural civilization at that time, both North and South around Central America. From Mexico, the southern parts of what is today the United States, down to Peru. And when the conquistadores arrived and then the Anglos arrived, they brought with them disease. Some of it was deliberate, but some of it was just that they exposed these people to pathogens they had not encountered. From this paper is estimating that the number of deaths, they called it the Great Dying. The Great Dying is usually referred to dinosaur extinctions, but they called it the Great Dying because this is the biggest death episode that we know about in history. 65 million people were supposed to have died in the Americas because of the European arrival. And what that meant was all that agricultural land and pasture land, because it was a pastoral and agricultural civilization, basically reverted to forest. So when you take a place where there's only grass and then you put trees there, all the carbon will come down. It'll just take a lot of carbon out of the atmosphere. And that seems to be coincidentally timing with the Little Ice Age. So you draw down CO2, you cool the atmosphere because that's the link. So CO2 is a radiatively active gas. So greenhouse effect, what is it? So this is a very early measurement, even back in 1857. So Eunice Foote basically said she had two bell jars, very simple experiment, and one of them she infused it with more CO2, and then she was able to prove that the temperature of the air there, just exposed to sunlight, was higher. And she speculated back then that an atmosphere of that gas would give the Earth a high temperature. But this is just a bell jar experiment, right? So we can ask about what happens here. So on the Earth, here's what it is. So the axis is tilted slightly, but basically the tropics receive more sunshine than the poles. So that's the way it is, because the plane of the ecliptic is around the tropics. So you have more solar energy coming in at the equator, and the deficit is near the poles. So more solar energy is radiated outwards. So If you think of it as a simple black body, it'll be radiating in all directions equally. But because the sun is coming in only around the equator, there is this difference. So now just simple energy conservation, somehow energy, which is the excess heat energy, which is in near the equator, has to move to the poles. How does that happen? Here's what happens. So you do that and you put Navier-Stokes on a sphere, and here's what you get. You'll get a circulation which says there's a trade wind circulation, so you'll get westerlies near the tropics. And they converge, as you can tell. They're both converging towards the equator. That pushes the air up, so that'll cause clouds and convection. So you have a green belt around the equator. All the air that's pushed up will go outwards towards the poles and come down. So where it comes down, you have fewer clouds because the air is pushing downwards. You don't get convection. So in the same zones in both north and southern hemisphere, wherever you go in the globe, you'll find deserts. So this Sahara will continue into the Thar Desert in India. And if you go in the opposite direction, you'll get to the Sonoran Desert in Americas. Similarly, you have the Kalahari here in Africa. And then if you go over here, because it's a higher, you'll get the Atacama Desert. And then if you go to so in Australia, the outback is also a desert at the same. So this is this is how the atmosphere tries to move energy from equator to pole. You do the same thing in the ocean. It's a little more complicated because now you have the continents. So the flow has to go around the continents. Some places the flow is blocked because it can't go and so forth. So what happens is you get the circulation, which some people call the conveyor belt. So a parcel of air, if you follow it, so let's start in the Atlantic. So a parcel of water will follow this line. It'll go along the Americas, and then it'll cross here. This is the Gulf Stream, the current that's known as the Gulf Stream. It goes up till here. So this is all warm water, which is going from the equator towards the pole. Here it becomes saline and cold, and it sinks to the bottom. So that is called the thermohaline circulation or the meridional overturning circulation. So it's sinking, and then the water returns along this path. It crosses through the Antarctic circumpolar current, and then there's this branch line for the Indian Ocean, and then goes up, and then again it returns to the surface in the Pacific, and then there is this. It goes through this region is called the Indonesian through flow, which connects Pacific waters to Indian Ocean waters. Crosses below the Cape of Good Hope, gets back into the Atlantic, and goes around here. This is a very, very slow circulation. If you follow that parcel of air that starts here, and then supposing you could somehow tag it with a die or something and follow it all the way around and come back, that would take around 1,500 years. So it's a super slow circulation compared to atmosphere. So now let's get to models. I told you that Bjerknes tried to build a model and he failed. And then a guy called Richardson came up with this theory. This is a very fanciful idea of what a weather model or a climate model would look like. He imagined that there would be a lot of people sitting in this globe, and each you can't see here, but every one of these places, there's a guy sitting or a guy or a woman sitting with a pen and paper. And when he shines a light on them, they will do a computation and pass it to their neighbor. And then he said, using this, we can do a calculation around the whole. When he actually tried it, he once tried a calculation with 64,000 people computing with pen and paper simultaneously. But he did not know numerical stability of Navier-Stokes. He did not know how to do it. So you have to figure out, like, there is a condition that tells you that for a given discretization, what is the maximum time step you can use so that your algorithm can execute forward stably. He didn't know all these rules. So his calculation gave nonsense results. So he also gave up. Then I told you this is Jules Charney here. I don't see von Neumann in the picture, but this is his wife, Eva Braun, who's supposed to have taught a lot of people computing as well. And this is how old computers looked. So Gopal went to talk to you about FPGAs, field programmable gate arrays, where you actually you program the chip will actually configure, the hardware can be configured on the fly to do operations in a certain order. This is what used to happen. They used to connect like the old telephone booths. They would connect wires from one unit to another. So this is what the old ENIAC computer looked like. Then we got into more programmable computers where you actually just wrote code on punch cards and all that. And then Manabe, who got the Nobel Prize in 2021 for physics a few months after I presented this talk, he worked in my lab. He was a colleague of mine. So he got a Nobel Prize in physics for building some of these first models. And you can see how fanciful these are, very simplified models of land and ocean, and they do these computations. And he showed the same result. that he says, okay, so Eunice said just by radiative arguments that if you put CO2, it's going to warm the atmosphere. So now what he's doing is he's got a 3D model of circulation on the atmosphere and the ocean. These dots are some observations. So this is temperature as a function of latitude. So if you use the base pre-industrial levels of CO2, which is around 200 parts per million, you will get this temperature profile as a function of latitude. You double that CO2 and keep running it, then you will get a warmer temperature. So this doesn't look like a lot, but if you look at it, it's actually a few degrees. So this is what we're talking about. It's the response to doubling of CO2. So Chani by then was a senior scientist. So about 10 years after Manabe's first results, people started saying, okay, maybe we should take this seriously for the planet itself. It's not just a fun result from a model. So he was asked to write a report called Carbon Dioxide and Climate, a Scientific Assessments. So GFTL, my lab, and then Jim Hansen, you might have heard of, he worked at GISS in New York City, the Goddard Institute for Space Sciences. They both had, by then there were 2 models in the world. So they did these things, and then they worked out a few things about how doubling of CO2, what will be. So the direct radiative effect, which is what Eunice was talking about, is not very big. It's only around 4 watts per meter squared. But you have feedbacks that amplify it. For example, if you raise the temperature, the air can hold more water vapor before it condenses. And water vapor is also a radiatively active gas, so it will also absorb heat. It will increase temperature. There is a thing called ice albedo feedback. So near the poles, there's ice, which reflects solar rays. It's white, so it reflects photons, so it cools the planet. If you reduce the amount of ice, you're exposing water, which is black, which absorbs water, so it'll increase. So the more you reduce ice, the more heating you do. So that's a feedback again. It's a positive feedback loop that increases the rate of warming. Clouds are an unknown question, because clouds, you can see that they can also, if you have a lot of clouds, they can reflect. They're white, they can reflect. But they also trap heat, because the heat that's underneath the clouds, they don't allow it to be released. So if you make a cloud field, will it be positive or negative? You have to actually do it. So the cloud distribution, he says, you have to solve the whole cloud distribution before you can tell whether the cloud feedbacks are positive or negative. And they predicted that for the surface warming, we are going to probably warm about 3 degrees. So this is 1979. So what we're talking about today is not new. We're talking about a result from, what is it now, 44 years ago. So this result, based on basic thermodynamics, and then you add in fluid dynamics, and you do the calculations, you do it again and again, you always get the same result. Keep adding CO2, you're going to warm. And for 44 years, we've basically taken no action about it. So if you go to today, there's a thing called the IPCC, the Intergovernmental Panel on Climate Change. They publish these reports. They say that, so these are 2 scenarios. So this is the historical period of warming. So these are all different climate models, all running the same calculation. And so then you can see if they're in agreement or not. So this is the historical warming. And then you can do 2 scenarios of what the future emissions trajectory might look like. So one, we'll assume that countries all get together and they regulate their CO2. So that's called the RCP 2.6, concentration pathway 2.6. And there you see it warms for a little bit, and then it stabilizes with around 1 degree of warming. The other one is that you don't do anything. You just continue with business as usual, continue to use fossil fuels for everything. Then you'll get to around 4 degrees of warming. So, and all the models kind of agree on what this, this is the uncertainty bound, but there is no ambiguity. That there is no confusion, there's no overlap between 2.6 and 8.5. There is until around 2050, but after that comes out. Now there's India, China, Brazil, Korea, all these countries have models also. So computing, let's go to the computing part of this. So this is the history of all the computers that my lab ever had. So this starts from IBM 701, which is 1956. At that point, Fortran did not exist. Fortran existed because people didn't know how to use the 701. So 704 was the first code I know, the first computer I know that ran Fortran codes. And computing power has been increasing now logarithmically. So this is scale 10 to the 10 scale of increase in computing power. And along the way, you can say the first simulation of the effects of doubling CO2 is happening around 1975. A model of chemistry, the Antarctic ozone hole was also done in the GFTL lab. How the ozone hole is formed and how it is now closing again. All these simulations were done here. So you can see various scientific results. So this kind of increase was pretty impressive, but we are kind of, if you look towards the end, we are starting to tail off from Moore's law, which is a doubling every 18 months.
So Balaji,
So all this, yeah. Go ahead.
along with this increase in computational power, I mean, in the end, what also matters is the input data that is being collected around the globe. Has that kept up, or has that exceeded, the increase in computational speed? And what's the trend in both of those?
Yeah, so that's a good question. So the satellite era begins around 1960. So these computers, the first calculations we're talking about predate Sputnik. Sputnik is 1957. So the first proper weather satellites are around mid-1970s, mid to late 1970s. I wonder if they are marked here somewhere. I don't see it. And resolution of satellite data that is used for weather models has been improving steadily. It's very episodic, Sanjay. It's not like you launch a NOAA GOES. The NOAA set of satellites is called GOES, GOES, Global it's something. I forget what the acronym is. It's global something. So those satellites, the resolution keeps increasing. So there's a satellite called MODIS, which gives you the highest resolution that has been used for the last couple of decades. That one has a resolution around 5 kilometers globally. So the resolution of models keeps increasing. The resolution of satellites also keeps increasing, and then they're not outpacing each other.
But what about the weather balloons and stuff? I mean, why, are those adding anything, or are the satellites good enough to do so?
No, that's also a great question. They're not good enough. We need the weather satellites, but we don't need to have as many, because we can use the weather satellites we have, which take vertical profiles, and use them to calibrate the remotely sensed measurements.
Okay.
So the satellites have to be calibrated using these in situ measurements with weather balloons, with local temperature readings taken at the surface of the ocean, for example. You can't do, we do some weather balloons over the ocean, but not a lot. But we also measure ocean temperatures. Ocean color is very important, because depending on the color, whether it's clear or murky, or whether it's blue or green, it absorbs different amounts of radiation. So these measurements, there's a lot of surface measurements which are used to calibrate remote sensing.
Okay,
So
thanks.
Balaji, do you create a mesh, and then you all these observations you put as data on that mesh? Is it something like that?
Yeah, but how do you put it on the mesh? So that's a good question. And how do you put it on the mesh? How do you fill in gaps? Okay, so supposing I have 3 data points, will I just interpolate? What will I do? So that's the problem that is we call data assimilation. How do you take these point measurements and improve them? So you need to run a model. Basically, you say that given this data and the equations of physics, what is the global distribution of temperature? You can't do one. Just simply measurements alone will not do, because you also have to say that they have to follow certain physical laws. Temperature and humidity have a relationship that they have to maintain. The spatial circulations that I mentioned about the trade winds, all that has to happen. So you can take measurements, but you need models in order to build these global maps on a globally discretized mesh. Exactly. Yeah. I see a hand up from Jayshree.
Yeah, I have like 3 questions. Just real quick. So, first of all, on the weather, you can't seem to predict more than a week ahead, and everyone complains that the weather prediction is not that accurate. So when we can't be accurate to a week, how can we be predicting stuff like over in the next 100 years and all that kind of stuff? That's one.
Yeah. Yeah.
And the second thing is that stuff they talk about, this butterfly effect. Is that something that's not? I mean, with the sensitivity to initial conditions, it's an important thing. Is that not an issue anymore with the computational machinery that we have?
No.
And the third question I have is, because of this weather getting hotter, you see some violent, weather patterns emerging, and are they a way of adjusting the recirculation so that things are going to cool down as a result?
Okay. So your first 2 questions are very closely related. So no, the system is chaotic, which means that it's got a sensitive dependency on initial conditions. So if you vary the conditions very slightly, you will get a different answer. So you cannot do an exact prediction. So Lorenz, Edward Lorenz was the scientist who wrote the first chaos paper in 1963. He worked at MIT. So he worked out what is now called the Lorenz limit. So given a set of nonlinear equations, how long does it take for the solution to completely decohere given a small change in initial conditions? So it's measured, you can measure that. So this is called the Lyapunov time for a chaotic system. So it tells you the amount of time it takes before it's completely forgotten the initial condition. It's in a state which has nothing to do with the initial condition. So it has completely forgotten about the initial conditions. So that time that it takes for complete decorrelation from initial conditions is about for the atmospheric system, it's around a week to 2 weeks. So you cannot do a proper weather forecast beyond about 10 days. Even theoretically, you cannot do it beyond 10 days. So why do we believe we can predict climate? So climate, we are not trying to predict weather, right? So we're not trying to say in the year 2035 on October 21st, what is going to be the temperature? We're not asking that. We are saying broadly is the climate. So we are reducing the precision of the question we're asking. We're broadly asking, how are the rainfall patterns going to change? How is the temperature going to change on average? It's not like weather prediction. We are just saying, given a certain scenario of CO2 emissions, how will temperature change? And your question about extreme, these we're getting these wild variations and extreme events and so forth. There is no evidence that those things are actively working to stabilize the climate. But the number of extreme events or the types of extreme events, there are some changes. And predicting those, what is the likelihood of Sandy hit New York in 2012. So what is the return period? When is how many years before we have to be ready for another Sandy? And is that time changing? So supposing what it used to be, so for bridge builders and all, this is the question. They often build for 1 in 100-year events. But supposing the 1 in 100-year event they built for is now going to happen once every 10 years, then they have to, recalibrate their baselines. So these kinds of things is what we ask about extremes. Are the likelihood of certain events, how are they changing with time? So I see that Garimala has his hand up and somebody else. So Garimala, I'm sorry. It's kind of very. I can't understand. It's indistinct.
Yeah, we can't either. So it's not just Garimala. Maybe it's your microphone or
Just put it in the chat.
I can't see the chat, so somebody should read it out to me.
Yeah, I'll read it when it's there. So continue till he puts the question there. I don't see it.
Okay, there was somebody else who had a hand up also, I believe.
That was beyond Jayashree. Let me see. Subodh? No, I don't think so.
Okay, all right. Maybe they took it down. It said that Srinivas Garimala plus one person raised a hand, but they've gone maybe now. Okay.
That was
that was me who raised the hand. I just lowered.
Okay.
Okay. So this is maybe an answer to how we have responded, how we have taken the computing increases, and so we're increasing the resolution. So this is Sanjay's question about, so the model, the satellite resolutions, imaging resolution is also improving. So that's also a fact. And these are various assessment reports. They were called the first, second, third assessment report, and then the fourth one is AR4, because after that, I think it would become FAR again. So they started using numbers. So you're increasing resolution, you're also increasing the complexity of models. So in the mid-1970s, you basically had rain, you had sun, you had CO2, and that was it. And then now we are saying we're adding the land surface, because the land surface itself is a sink. So there's an effect called the CO2 fertilization effect. As you keep increasing CO2, the rates of photosynthesis go up. So plants become more efficient at taking the CO2, which is a stabilizing effect. It's a negative feedback. So they're drawing down CO2.
There's a related question that Garimala was trying to ask, and I'll just read it. He says, you mentioned cloud cover. That has a very small time scale compared to your other bigger, I'm adding that. But So do we need to actually model clouds in detail, or can we just take an average and move on?
That's a fantastic question. So we cannot model. So look at these resolutions here. We're talking about, if you look at far as 500 kilometers and becomes 250, 180, 110. So the resolutions are not increasing that much. So AR4 is 2007, we're at around 100. So AR6 is what we just did, 2019. We are at maybe 50, some models are doing 25. Cloud processes are taking place at very small scales. So deep convection, which is like the big thunderstorms, you need about a kilometer scale to resolve that. And shallow clouds, which is what these big cloud banks you see, huge, off the coast of California, you see these huge banks of shallow clouds, stratus clouds, which reflect a lot of sunlight. Those to actually simulate their boundary layer clouds, and the boundary layer is about a kilometer deep. You actually need to get your resolutions down to a few tens of meters. So yes, you are not going to resolve clouds. So the clouds are solved using what we call parameterizations, where we make some statistical assumptions about what a population of clouds within a grid box that's 250 by 250 kilometers. You assume that there's a population of clouds, and they exist in some kind of quasi-equilibrium with the mean atmospheric conditions, and you try to predict what the aggregate effect of all these clouds will be. So this is a huge problem with our models, actually modeling the clouds, because we are never going to, resolving cloud dynamics is very hard. That's what I did my PhD on, by the way. So today, a model has around 25 kilometers and about 100 variables. So you can see, so there's all kinds of chemistry, and then within plants, you can have different kinds of plants, grasses versus trees. They process CO2 differently. You go to the ocean, you have phytoplankton, which do photosynthesis and absorb CO2 also. And then you have zooplankton, which are critters that eat the photoplankton. And then as they die, they can sink to the ocean floor. So that's one way. So the ocean is also a sink of carbon. The land is also a sink of carbon. By the way, of all the carbon we emit, only about half stays in the atmosphere. About 25% disappears into the land, 25% disappears into the ocean. We don't know whether that will continue, but that's the current rate. In fact, many people are thinking that the rate at which ocean and land can absorb CO2 is going down, which means that there'll be a rebound effect that will increase the rate of warming because it will stay in the atmosphere. So does that cover most of the questions? I hope. Let's keep going.
Yeah,
So
I
the
think keep going, and because it's lateness of the hour in India too that'll hit us. So let people benefit from the rest of your talk, and I think we'll ask the rest of the questions at the end.
Okay, let's do that. So the other thing we can do with models, which is very, very important that people don't often think about. So we think about models as a way of prediction. Models is also a way of generating what we call counterfactuals. So what would happen if all the CO2 warm disappeared? So this is a study of the Indian monsoon. If you look at this gray bar is a set of measurements. A lot of these are measurements, but there's a sense that the Indian monsoon has weakened over the 20th century. The strength of the monsoon has come down. So you can do simulations in different ways. You have different forcing agents that will tell you, so you can add one. So there are different kinds. So there is the black line is the measurement. If you put all forcing, so let's see what a forcing is. CO2 is a forcing. It's an external thing that you add to the atmosphere, and you see how the atmosphere responds. Sulfates and particles and all black carbon particles, soot particles, these are another kind of forcing. The atmosphere will react to how much you put in there. So these particles, we call them aerosols. The CO2, etc., are called well-mixed greenhouse gases. That includes ozone. O3 is mentioned here. And then there's natural stuff, which is like volcanoes, which will throw up dust into the atmosphere, things like that. So to run a full climate model, we do all the forcings put together. So you have the aerosols, you have the greenhouse gases, and you have the natural forcings, volcanoes, etc. So that is the red line. So the red line is the models are doing a pretty good job of predicting the weakening of the monsoon. And these dashed lines, by the way, are just taking this noisy time series and just putting a slope on it. So it's a least squares slope of that line. So it's showing the weakening. If you just put the greenhouse gases, so you're just saying, what is this is why we call it attribution. How much of this is contribution from CO2 and how much is the contribution from aerosols? These kinds of questions you can only ask with models because there's no way to observe these things in nature. If you only put CO2, you're seeing the it's actually, that's the purple line. You're actually seeing the strength of the monsoon increasing. So you need to include the aerosol. The aerosols is giving you, that's the green line, that's showing you forcing, and the volcanoes seem to be kind of neutral. They're just wiggling up and down. Maybe there's a slight decline. So this is the way, this is what we use models for. We're also asking questions about if the forcing's changed in this way or that way, or if you, how much of this warming is due to methane versus CO2. These kinds of questions we can ask with these models. Now, here's where we get into the recent crisis. I'm going to go fast now because I realized that I'm taking a lot of time, but I hope the questions have kept it interesting. So this is where the connection is with probably with what Gopal talked about last week or a few weeks ago. So Moore's law said that we're going to keep doubling. So this is a logarithmic scale starting from the 1970s. They keep going, the number of transistors, the density of transistors keeps increasing at a logarithmic rate. But the crisis in computing for us, for the people who solve equations, is that what's the frequency, which is reported in megahertz, has stalled at around a gigahertz around a decade ago. So a single arithmetic operation is still stuck at a gigahertz. It means it's a 1 nanosecond per is the clock cycle. You can do one operation per clock cycle. That operation itself can become more complex. You can do like, multiply and add at the same time and so forth. So that is stabilized. The power it takes is stabilized. These things are all, they're not going up faster. So what you're doing is you're just adding more and more items in parallel. So we have had to transform our algorithms to go from relying on arithmetic becoming fast to being more parallel. So that is a big, with the end of Dennard scaling. And this is, by the way, a physical limit. So Dennard's paper is actually dates to 1974. And he basically said, as you keep shrinking the size of a transistor, because the transistor is smaller, the speed will go up. So there's a table of calculations you can do. What he showed was that the power density, which is the density per unit area on the chip surface, will stay constant. So you can keep bringing it down, and he says the power requirements will not change. That's what gave rise to Moore's law, because we are following Dennard scaling. Dennard scaling starts to break down once you reach around, let's say, a 7 nanometer fab. We're just beyond that now. We're at around 5 nanometers. TSMC Taiwan, which is the only place which does fabs these days, is saying that they may be able to get to 4 or 3, but I think we're pretty much at the end. We're not going to get any smaller transistors anymore. Maybe Gopal will disagree, but that's my understanding. And then there are different algorithms which are not just gated by the actual speed of the arithmetic. In order to do the operation, you also have to feed it from memory. So the memory speed also matters. So this is, again, it's a few years old data, but there is this kind of diagram which is called roofline diagrams, which is again showing how many operations on a logarithmic scale you can do per word that you pull from memory. So in order to do one operation, you have to pull a word from memory and then send a word back with the result. If you're gated by memory, you will be on this sloping part of the roofline. This is called the roofline model. And if you're at high operational intensity, which means that for every word you pull from memory, you can do a lot of arithmetic, you will reach the peak, what the chip is capable of. So there are some algorithms. One here, this is called the fast multipole method. It's really efficient, so they can use all the power of the chip. Most partial differential equations use what are called stencil operations, which means that you're only pulling data from nearest neighbors. So you're computing a horizontal difference, let's say, things like that. You have to use a lot of memory to do one calculation. So we are not very efficient. It's a nature of the algorithm. It's not because we don't know how to code. They don't get very fast. And then this is just showing you different kinds of machines that are coming in, and then there's a set of machines. And this is all, by the way, completely the NVIDIA revolution has completely taken all this. These slides are all obsolete. And then EU and Japan are moving forward with a kind of chip that's called ARM, which might still happen. ARM is NVIDIA tried to buy ARM, but they were blocked by the EU, which is a good thing. And machine learning. So this is why we are moving to machine learning. So most of the chips today, this is from NVIDIA, but this is from a couple of years ago. But they predicted that doing what we call traditional high performance computing, which is the kind of models I'm talking about, they believe that they will, they work with, first of all, we need to work with floating point with a lot of bits, 64 bits of floating point. That means like 15 decimal digits of accuracy. The size of the market is small. Training deep learning, which can be done with much smaller, with only 32 bits, which is around 7 decimal digits of precision, is a bigger market. And then inference, which you can just do with integers, the biggest market is there. So they basically, all their R&D shifted towards the right. They work with short words, and they try to do a lot in parallel. Data center energy cost is something we worry about also. I'm going to skip this slide. So this was a question Garimala asked earlier. So as we keep increasing if you get to from petaflops to exaflops and so forth, the resolution of the model keeps coming down. And you asked the question that was asked was, what can you resolve? So if you get to somewhere down here, you're resolving thunderstorms, which is like big convective systems, but you're not resolving shallow convection, which is the boundary layer clouds I spoke about, or you're not resolving tornadoes, which happen at 100-meter scales. So you can't resolve these. And in order to do the climate runs, which is like actually trying to see how it will change over 100 years and so forth, you had to run like thousands and thousands of simulated years. So it's very unlikely we'll directly do these on any computing that I know exists, which is anything that is silicon-based, anything that is based on CMOS or MOSFET, even FinFET, we're not going to be able to do the volume of computing we need on any computer that exists. And then also we're computing the carbon cost of running these models. These models take a long time to run. They stay on a big supercomputer and they run for months. So we're computing the carbon cost of that. So this is a group of people who argued that we can actually go to high resolution. So they proposed it as a kind of Turing test. So if you look at the original Turing test, he said, like, by just simply exchanging messages with the computer, will you be able to ask it a series of questions? Can you tell whether you're speaking to a human or a computer? And of course, these new large language models have largely passed the Turing test. I think many humans will fail, but that's a different story. So the same question you can ask, I'm showing you all these images. Some of these are from a satellite, some of these are from a model. Can you look at these images and say which one came from a satellite, which one came from a model? It's really hard to tell. Of course, somebody from the field will be able to do some computations and show that one of them is not doing cloud fields accurately, but visually you can't tell. So you can say that we have kind of passed the Turing test at some level. But what we're really trying to do is to increase the density of arithmetic we can do, because that's what these new chips are very good at. So why do we why do we like deep learning so much? It's because let's take an input layer which has 5 points and an output layer that has 4 points. If you want to simply compute a regression between those, let's assume just between 5 and 4, you'll have around 20. It's a matrix inversion around 20. If you add a neural hidden layer in the middle, each black line represents one of these arithmetic operations. You can see that you vastly increase the density of arithmetic. Instead of 20, you now have, I can't do the calculation in my head, but 5 times 7, and then that's 35 times 7 times 4, 28. So it's 35 times 28. So instead of 20 computations, now you've increased it to this 35 times 28, which is 2 orders of magnitude higher. And the more layers you put, the more you're increasing the density of arithmetic. So you can do dense linear algebra. If you can cast all your problems to look like dense linear algebra, you can do very well on these GPU machines. So we're doing a lot of work trying to do this, what is called coarse graining using machine learning. So you have this cloud field. So this is a very high resolution simulation. It has been run at, I believe, 3.5 kilometer resolution. But your climate model is going to run at 100 kilometer resolution. So it's going to have a resolution that looks like this. So you take the data from here, and inside each grid box, you say, here's a distribution of clouds. And then you try to work out, you just use machine learning to try and compute these things from these global models so that you can, so it's called coarse graining. So it's like reducing the size of the computation you need by using machine learning to compute the relationship between high and low resolution. So this is what one other machine learning example. So what machine learning does, so this is a variational technique called a variational autoencoder. It takes something like, let's say, a face. You want to do facial recognition. it takes that and then it runs it through a series of computations so that you come up with a small feature vector, which is very as sparse as you can make it, the smallest length of number of features. And now you've said that any phase is some linear combination of these features. So from that, you can generate new phases. You can generate synthetic phases. So if, for example, you can take this is an actual phase and that is an actual phase. You can compute a phase that is the average of those two. You can do it by using these features that these autoencoders give you. So we can do the same for physics, right? So this is what we're trying to do with model reduction, right? So we are trying to reduce it to a number of features, and then we're trying to say that I'll do all my computations with the features, and then from the features, I can go back and reconstruct these high-resolution models. Why we need to do that is, again, I think I'm just repeating a point that I said before, is that we have a lot of different kinds of uncertainty we need to solve for. So one is the question that one of you asked earlier, the chaotic uncertainty. So if you're not trying to calculate exact weather, but you're just trying to calculate something like the decadal mean surface temperature, so it's a highly average quantity, global mean, and then also average over 10 years. So the effect of chaos basically diminishes with time. So you don't need to worry about it once you go beyond a certain time. What we really don't know is the green uncertainty, which is called the scenario uncertainty, because it's based on what policies humans will do. Will we act to go back to net zero or zero emissions or negative emissions, or will we not do it? That depends on politics and all that. And we are not trying to forecast that. I think that would be a stupid thing to do. And then there's a third thing, which is called structural or epistemic uncertainty, which is that there are some things about the climate models. We discussed clouds. We are just trying to say that there's a statistical aggregate of clouds without actually simulating them exactly. So that kind of uncertainty also exists. So this paper is basically saying that we need to sample all these kinds of uncertainty because the fraction of uncertainty that is described by these different kinds of uncertainty remains important for long periods of time, decades. So these are all counterfactuals. So again, it's worth emphasizing. We do not have any measurements. We cannot directly observe what will happen under 4 times the CO2 because we cannot do that experiment on the real Earth. So we are reliant on simulations. So we need to run hundreds of simulations in order to do this. So we are still stuck with this computation as being a basic restriction on problems. So this is maybe a little too technical. I'll kind of skip this. We'll go back to, I'll just end with this. So we talked a little bit about paleoclimate, and somebody asked, are we able to simulate the fact that the temperatures are high near the poles? So this was when I showed the original slide, and actually we don't do this. So these 5 or 6 these things are data points. So these are observations. So we are fairly sure from doing this kind of measurements of isotope ratios in shells and so forth that in Antarctica we measured 17 Celsius and near the North Pole we measured 23 Celsius. So it was quite warm near the poles. This is what is considered what we call an equable climate. So the temperature gradient between equator and pole was not very high. It was only 7 degrees. Today it's around 40 degrees. All the models are actually predicting a high temperature gradient. Do you see the configuration of the continents here? So India is still only halfway to Asia. It has just broken off from Africa and is sailing in this direction. The Americas are not joined. So the Atlantic and Pacific are connected here, which is not the case today. And the Mediterranean is open. So there is also through flow here. So this is, we're fairly sure that from the tectonics data that we know what the configuration of continents was. But you put all that in, and you run your model, and you don't actually reproduce the data that you have. So our models are kind of not yet ready to solve really. So we are not. I mean, we are certain about the results that the temperature is warming and so forth, but there are some things the model still can't do. So where are we going? So let me just summarize. So we are trying to simulate the Earth system as much in as much detail as we can. Why should you trust them? You trust that the individual processes because you can take measurements and you trust the feedbacks. You trust physics, basically, the laws of physics. So you have many lines of evidence and you try to make the models match all the lines of evidence you have, whether it's tree rings or isotopes or balloons or satellites. There is an article, there is a story by Borges, he's an Argentinian novelist. So he wrote a story about, it's just a one page. The story is called On the Exactitude in Science. If you do a web search, you'll find the entire story. It's less than a page long. He says there's a country in which the cartographers, the map makers, first said that I'll make a map of the country which is 1 to 10 scale. So it'll be a tenth of the size of the country itself. And they did it. And so then they became more ambitious. And they said, we're going to build a map of the country which is a scale 1 to 1 with the country itself. And then in the story, the leaders, the king of the country basically say, I don't see the point. They build it. And then he says, I don't see the point of it. So they abandon the project. Because I mean, honestly, what do you do with a model that is 1 to 1? If it is as complex as the Earth itself, then understanding the model is as complex as understanding the Earth. Lewis Carroll wrote a similar story also about these Sylvie and Bruno. They're going hiking in the country, and Sylvie says, I heard you have a good map. He says, yeah, I have a map of the country that's 1 to 1. She says, why didn't you bring it? Then we won't get lost. She says, well, I can't carry it. So then the other question is these AIs have we are trying to show how we can use machine learning to replace, the physics part of models. Supposing there was no physics at all and you just did machine learning, and by the way, we've reached that today in weather. There's a DeepMind and OpenAI and all have started. No, not OpenAI. DeepMind and Google and one other company have started issuing, NVIDIA, they've all started issuing actual weather forecasts, which are run by simply deep learning inference. So they've trained it on 60 years of, 50 years or so of weather data, and then they just run inference. With machine learning, there is also this issue that there is a hype cycles, there's a publication bias, positive results are published, negative results are not published. Most of these models don't publish enough of their weights and the way they trained it and all that for other people to reproduce their results. But I know it's not all hype. There's a lot of really good results there. So I'm following a lot of work that's using machine learning. And of course, the hardware has gone there, so we don't have a choice. We have to follow the hardware. But you have to remember that you must be capable of going outside observational bounds. So you cannot just train on data, which is a conundrum for machine learning. You can only be as good as your training data, but climate is changing. So you need to be able to go outside what you can observe. So what we try to do is we build these things called hierarchies of models. So we try to build simple models from expensive ones. And machine learning gives a very good way of doing that. It's a very formally correct way of not simply trying to look at the equations and figure it out, but actually derive simple models. So I think I'll stop here. So I kind of finished, went about 10 minutes over time, but if there's people still around, I can take questions.
Oh, thank you very much. SAP had told me there's no time limit, so you didn't go 10 over anything. It was all us asking questions. So let me try and look at what the chat questions have been. And I'll just start from the top. There's a question from Sundar Ramachandran. How important is methane? How localized is our capability to locate fugitive emissions?
So that's a great question, Sundar. So methane is very important because molecule for molecule, its greenhouse intensity is higher than CO2. The absolute amount is smaller. There are a lot of point leaks. So can you detect them? So there is a program called Climate Trace, which is funded by the Gates Foundation, which is trying to look at satellite data to locate methane leaks. Satellite data of carbon to locate methane leaks. It depends on a lot of crunching and AI. There's a lot of machine learning involved as well. So it's possible that we will be able to locate point leaks and identify them. But at this point,
the reason I'm asking is that it should be easy to prevent fugitive emissions if there's political will. And a lot of people, including my company, have technology to prevent that. We actually advertise something that tries to prevent it. However, And again, one of the reasons you do sometimes have fugitive lakes is it's the easiest way to perhaps begin production of gas wells, or unlock things like that. But you could go to flare. There are a lot of other options an engineer could do, but this would be the cheapest option. Again, if there would be a case of policing, but I guess the politics of it no one would allow policing.
Can we just stay with questions?
Yeah. Oh, sorry. No, that's just an issue on the thing of, because I think that's that's a very simple kind of technological fix on a little bit of the problem.
Yeah, but I think you put your finger on it. At this point, nobody is, there's no disincentives for leaking. So nobody's going to do it. So we have to assign. So the key issue from the policy perspective is, how do you actually assign carbon cost? How do you actually start making carbon has become, in almost all economic modeling, has been treated until very recently as an externality, because nobody's paying. It just goes in. It's what's called a well-mixed gas as well. I mentioned that on one slide. What that means is that its residence time in the atmosphere is very long, and then the molecule of it's so long, it's 70 years. So it doesn't matter where it comes from. The effect is global. So there is no point saying, that I'm not going to worry about Chinese emissions because it's China's problem, all that, because everybody's emissions has become everybody's problem. And it's in fact most of a problem for countries that do not emit much CO2. So the big emitters are, that's why it becomes an externality. The big emitters don't care because everybody is paying an equal cost for the warming. So until we put something in price, which is, this is what I'm trying to work towards now in my new job, which is to how do we actually get the measurements to a point? And it also relates to, I've got the chat up now, by the way. So Jayashree's asked the question, is the carbon cycle fully understood? It is not. So very specifically about the carbon cycle question, annually we publish something called the GCB, the Global Carbon Budget. There is a hole in it of 1 petagram carbon per year. That means that if you add up all the known sources and all the known sinks, it's not adding up to 0. It's adding up to -1 petagram of carbon per year. So there is something missing. We don't understand it fully. We have done the work to say that if we can get that, fix the missing carbon and also get the precision of the carbon cycle down by 1 order of magnitude, not more than that, to 0.1 petagram of carbon per year, then we can actually start doing some of these things where we can trace and say we can do carbon. I talked about attribution, saying how much is due to carbon versus how much is due to aerosols. We can start saying how much is due to emissions and where they're coming from and so forth. So yes, it's not fully understood, but I think we can define a research program to answer that question within, let's say, 5 to 10 years. That would be my answer to Jayashree's question. Oh, Srinivas. Okay. All right. Great. Then I don't know which order I'm going in, so I may be going out. Sanjay, why don't you ask me, because I may be going out of order.
Yeah, and I don't want Talia to hog all the questions. We can come back to his questions. So one of them, Shirish Netke asked, how are climate models used for risk modeling of economic scenarios? So I think you talked a little bit about scenario modeling, but are there specifically concluding economic scenarios from this?
Yeah, so the problem with that, I mean, yes, I think the short answer is yes. So specifically, let's take the insurance industry. They're using climate models. They're actually running. They're hiring people from my field, so I know that they're running in-house climate models. They're trying to assess risk. Once again, the issue is that insurance is structured so that premiums are updated once a year. So they do not have a mechanism for planning beyond a year. So my short answer is people are looking at climate risk on fairly short timescales. So one of the big activities in the conference I'm at in Kigali is we are trying to get a systematic program going on climate risk that people can actually take into account in investment and decision making. It's not there yet. So the Biden legislation that has been pushed, which requires a certain amount of climate risk reporting as a requirement in your annual company audits. These are all movements in the right direction. So a lot of it now, I think, it's a very recent phenomenon, which I'm going to present as an optimistic scenario. We've gotten to the regime where these policy discussions are becoming real. Until a few years ago, especially in the US, we were basically in denial. In fact, it's still the case. I mean, in one half the population and half the political class is still in denial about it. They deny that it even exists. But the basic debate has moved on from there right now.
So Balaji, this is Shirish. It's gone a little bit beyond the insurance industry right now, to the extent that financial institutions and banks are looking at it, and at a much more rigorous level. So insurance companies have historically been looking at risk, but there is a lot more financial institutions looking at it now. And the question to you is, have they been in touch with the climate scientists about this, or are they? I don't think they're relying on the insurance companies anymore to protect the financial risk.
They're not relying on insurance companies. I just use insurance as an example because the risk argument is clear why they would be interested. So yes, a lot of financial sector companies are interested in looking at climate risk, because if you're making an investment in a place which is going to be, let's say, if you're making a big investment in Miami real estate, it may not be a great idea. So these kinds of things they're starting to take. Investment banks are also starting to take into account. To my knowledge, this is very anecdotal because this is not where I work in, but from speaking to people at BFA, for example, they are relying on third parties. There's a whole cottage industry that has sprung up for people who will do a risk assessment on behalf of clients. So that industry is growing. It's not yet a regulated industry, so there's a bit of Wild West quality to it. People will tell you that, and I told you some basic limits on forecasting capability. There are companies that will confidently tell you they will do forecasts for you of summer temperature in 2035. So yes, so there is a somewhat unregulated industry of some players whom I know to be fairly serious about it, and some who are selling snake oil.
But are there these financial companies at the conference you're in?
This is the climate science conference, so there may be some, but I don't think that the bulk of it won't be that.
I think, Balaji, my question was more of how, let's say, relevant or accurate are the results from climate models for financial modeling? Are they like just one piece of the puzzle? Are they meaningful enough that can be used for financial modeling?
Yeah, so you have to ask the right question. So if you're asking a very, very local question, usually our models are not good enough to give you local information. But I can tell you broadly, for example, that the Southwest United States is going to be in a water crisis for a fairly long period of time. California has an extended drought. Australia has an extended drought. So you can make broad statements like this there. You have to learn how to use those. You should not expect exact predictions for Phoenix, if you know what I mean. So you should say, but if you can take a result for the Southwest and then make decisions about Phoenix, that's fine.
Okay.
All right. There's a question from, I want to favor the Indian questions since the interest of time. I'll switch to the other countries later. But Pankaj has a question about, though the trend line of the Indian monsoon may have weakened over time, we seem to have more extreme rainfall events like cloudbursts or very heavy rainfall in short periods. Briefly, why does atmospheric warming cause more such extreme events, if that is indeed the case?
That's again a great question. That seems to be the case. So the same amount or maybe a slightly lesser amount of rainfall, no matter what the mean amount of rainfall is over a monsoon season, the number of rain episodes over which it happens is now, each one is more intense. So the average rainfall has not changed much, but the intensity of rain events is definitely increased. And we are still arguing about the exact causes of that, but the warming is definitely a factor in that. There's no two ways about that. So any model that has warming seems to be showing this kind of larger fluctuations between within one monsoon season. There are dry and wet periods which are more each is more intense than it used to be.
Pankaj, are you still there? Did that address your question?
Yeah, it does. So what I understand from what Balaji is saying is that probably the observation is correct, but the reasons behind that are still to be really found. Thank you. Thank you. Great talk, Balaji.
Yeah. Pradeep has a question. CO2 levels are around 400 plus ppm. Is it latitude, altitude dependent? Is this value an average around the world?
Yeah, so what it is, it's not, yes, of course it is latitude, and on a short time scale, I mentioned that it's a well-mixed gas, so over a period of decades, it goes everywhere, but over a short time scale, it's also local, close to where the point of release is. What this measurement is there is one continuous set of observations that has been taken since 1950 in Hawaii in an observatory in the Mauna Loa. So it was started by a guy called Keeling, so it's called the Keeling curve. Why that observation is important is that it is very far from any source of CO2. So it can be taken as a representative of the global state. So that's what that 400 ppm measurement is a measurement at Mauna Loa.
So Srinivas had a question, and it's related to the financial model, etc. How does one set the carbon penalty rates given the uncertainty in climate models?
Yeah, great question. I don't think I don't think I know the answer to that. So so eventually we'll have to peg the price to something, and we are not sure what yet. But starting with a price, even if it is a low price, starting with any price at all. I mean, many people are basically saying, I mean, I'm going beyond this thing of just arguing with climate deniers. I'm not interested in arguing with deniers anymore. Let's say we've moved the debate beyond that. But even among the non-deniers, people who want to do something, they're saying we would like to do something, but we need a price signal. Without a price signal, we cannot factor it into our financial planning. So any price is better than no price at all. Let's start with a low price. And then we can start building these institutions, for example, so there are technologies emerging for drawing down carbon. Okay, so how much do you get for that? If you successfully sequester carbon and bury it in the ground or in the ocean, what should you get per ton of CO2? What should the price be? Eventually, the market will set it, of course, but you have to start with something that actually assigns a price to it. And then how the market will emerge. Now I'm speaking well outside my expertise because I know nothing about financial markets. So, but this is recent stuff for me. How the carbon market will emerge, in my belief, is that you start with a price so that people will start doing stuff. People will start building these industries. Eventually, we will get to a regime of carbon accounting and auditing, where every product that is built, you will get a detailed audit of every element that went into it, what the carbon cost was. And once people start assigning a price to that, there will be disincentives for the use of carbon. There will be, movements towards, trying to move towards less carbon intensive methods and all that. But you have to start with some price signal so you can kind of bring this industry into existence. Right now, it doesn't really exist.
Yeah, that
There
could
is
be
no
a long
regime. There's no global regime for carbon accounting, auditing, and none of that exists.
Saurabh had a question about, you mentioned that around 1600, when some 65 million people died, the tree cover increased and the temperature came down. But Bill Gates recently said that planting trees will not get us out of the climate crisis.
Yeah, I think Bill Gates is right, and I'm right also. I mean, no, I'm not right. Cockatell is right. I didn't have anything to do with that work, so I'm just citing other people's work. But many people are seeing this as an easy fix to the problem. Who doesn't like to plant a tree? Sab log jao. Everybody has these things where you go out and you plant a tree, but then you have to make sure that the tree comes to full height and then it stays that way. That there are, but that it depends where you plant them. and then there has to be enough water for the tree. You have to make sure it doesn't die. So let's say you have a carbon credit regime, right? Like I'm imagining. And you plant a lot of trees. You claim a carbon credit. Many people are doing this actually. Plant a tree, you claim a carbon credit that I took. When the tree goes to full height, it will represent X tons of CO2 taken out. But what if the tree dies 10 years later? Or what if there's a forest fire? So simply planting trees, because once you simply just even taking into account the water requirements for all these trees, so you'll find that a lot of people who are claiming they will plant trees, trillion trees and so forth, you'll find that there's not the land surface cannot support that many trees.
I mean, people shouldn't stop planting trees. Is that?
No, there's no reason to stop. And planting trees is not a bad thing at all, but it's not going to fix the global problem.
Okay.
So
Garimala,
to put a figure on it, we need to be able to take around 12, if I'm not mistaken, something like 12 gigatons per year out if you want to stabilize carbon, just stabilize carbon.
Subodh had a comment, which is interesting. Many thanks, Balaji, for superb talk. I am working on public finance solutions to climate change. So I was able to relate your modeling studies results. Excellent. That's just a comment, but I thought I'd pass it along.
Okay, thank you. Thank you, Subodh.
Saurabh Prakash, how much can carbon sequestering solve the climate problem?
Yeah, so it's got to be a mixture of two things. One is emissions reduction, which we do not want to go there. Most people are trying very hard to fight that. In particular, Saudis and UAE are in the recent G20 meeting in India. There were Saudis fought heavily to take out any requirements of emissions reduction. So they want to say that carbon reduction is going to work, so there is no need to reduce emissions. So that's one line of thinking that is being promulgated by the fossil companies. But there's a lot of calculations showing that we do not have any technology that exists that can. I was mentioning the numbers that involved. So we're talking about some things that is measured in tens of gigatons of carbon taken out per year. So we are working with some very small scale solutions, but I know of nothing that can scale up to that kind of number. So emissions reduction and carbon reduction are both going to be necessary, and carbon drawdown are both going to be necessary.
Okay. Garimala had a question. Most of the feedback mechanisms usually highlighted, like you did in your talk, are the positive feedbacks. Is there a level of warming at which negative feedback will start tempering the effects and stabilize the temperatures?
Yeah, that's a good question. I don't know if there is something where it will naturally start to stabilize. I mean, I showed you some curves. They seem to just keep increasing for, they didn't seem to be leveling off necessarily. So I showed you out to 2100. Some people do run these simulations out to 2400. They don't, if you keep adding CO2, so there is one interesting thing, which is that despite the fact that this is a highly nonlinear system and all that, and all these feedbacks and everything, one thing seems to follow an exact straight line. The temperature follows the amount of carbon in the atmosphere on a fairly straight line. So if you say that, I don't have the curve in my talk, but you can look for it, you'll find it. So there's a fairly straight line that shows if there is so much CO2 in the atmosphere, what will the temperature be? That prediction is fairly good. And I do not see any signs of it leveling off.
Yeah, in fact, again, it's a feed forward kind of thing, but at some point, the large storage capacity that we've been leveraging from the oceans, etc., once they get warm, they will start, releasing that carbon dioxide into the atmosphere too.
Yeah.
So it's just a feed forward kind of thing, but I had not thought of any negative feedback systems which kind of stabilize. But
exactly. So that's a good point, Sanjay. So one of the key questions we're interested in, which is actually the most troubling for me, like keep me up at night kind of question, is what is going to happen to the land carbon sink and the ocean carbon sink as we keep adding CO2? Can they continue to absorb? So right now, as I told you, for every 100 tons that goes up, from emissions, 25 goes into the ocean and 25 goes into the land. And only 50 stays in the atmosphere. So half of it is taken out now. If that half fraction drops to 40%, 30%, 20%, 10%, then we are really hosed. I mean, we're going to be in a great deal of trouble because the rate of CO2.
Does the 25 include what, I mean, is it directly going into the land, or this is due to trees and forests and stuff?
Yeah, and it's also due to this thing which I call the rates of photosynthesis increase. Plants become more efficient at taking CO2 out.
Okay. So I know Gopal.
And then soils. I'm emphasizing plants, but there's a. By the way, let me just. I mean, this is a complicated problem. So there's a huge reservoir of below ground carbon on land. The carbon sequestered below land is 4 times bigger than the carbon sequestered in trees. That is, I'm saying that it goes into root biomass, and then from root biomass there are these fungal networks that take it out and then mineralize it in soil. So that number, I'd forgotten the actual number, but the number of petagrams of carbon in soil is 4 times bigger than what is in trees above ground.
Yeah. Gopal, you had raised your hand and had questions about AI or comments about AI. You still here?
Yeah, great. Balaji, thanks for a great talk. Couple of questions about AI. I didn't quite get what you said about the gridding story. So can't we take the models as, are you saying they take models outputs as coarse grids and then use ML to refine it using this data, because then you can scale the problem? So that's one question. The other question related to it was, this is a dynamic system and you probably are using something like a recurrent neural network where states are stored. And recurrent neural networks have been replaced by transformers, which is the talk of the town. So that seems to be like a very potentially a good outcome for your work, because you should be able to use transformers very efficiently.
Yeah, people have done that already. So people have built foundation models for climate. But the problem is what they're relying on is around 30, 40 years of data. And within that data, it is, I mean, normally when you're doing training, yes, this is exactly the way it's done, Gopal. So we are starting with RNNs, and then we can replace them now with transformers, which parallel. So for people who are not in the loop, so recurrent neural networks if you have a time series, they will learn each step they will keep learning as they go along the time series. So they will learn from the first few, and then they will keep refining that as you go along. What transformers do is that instead of doing it sequentially, you can now do it in parallel by basically sizing context windows from where you train on subsets of the data, but instead of doing it now in sequence, you can do them all in parallel. So that kind of work to build foundation models is done. So the problem is that typically when you're doing this kind of training, if you have 40 years of climate data, you will say that year 1960 and year 2018 are the same. Each one is a sample. But here there is also a trend. So that makes this problem a little more complicated, but yes, the work is going exactly in the lines that Gopal is describing. So we're trying to use transformer-based foundation models for climate. We're trying to build those right now.
Balaji, my question also is, so why can't you run your models and use that as your data source?
Yeah, that's
synthetic data, right? It's effectively synthetic data for future
that's
training.
What we're doing. So, yeah. So, so sorry to cut you off, but so when I'm saying data, I actually mean the output of weather models. So as I said, I mean, the observations are here and there, right? So we got observations which are scattered around the globe, and then there is satellites are sampling it from space, but not intermittently. I mean, the return of passage over the same pixel is some measured in days. So somebody asked this earlier. So we have point measurements, and then we use models to fill in and make a 3D gridded or a 4D gridded data set, including time. And then you learn from that. So you are learning from essentially synthetic data.
Oh, thank you, Balaji.
Yeah,
Great
so
talk.
we are, so the high, you also asked a question about high to low resolution. What I was saying is that you can run high resolution models, but you can't run them very long because it's too expensive. But if you create enough high resolution samples, one of the utilities of that is it produces a large volume of synthetic data that you can learn from. And then the challenge then is to learn low resolution models, to coarse grain it. So you learn what is a smooth underlying solution from this kind of noisy high resolution data. That's what you're trying to do.
Okay, great. Got it. Thanks, Balaji.
Thanks, Gopal.
Just a quick question on something you said. Just because there are trends, I mean, and you know, the neural networks can handle having different time cycles in them, though, right? I mean, the ones that handle time series. So is it? I don't practice this, or I haven't done much of this ever in my life, but I would think trends are par for the course in the sense that it's not a static time series. There are some trends going on, and you should be able to incorporate that into your models. Is that not true?
Yeah, I had a slide on that actually. Let me see if I can just bring it up again. So here you go. So we did the study some years ago. So if you train on the data from, so what we did here is that we are producing high resolution data for the future. Basically, we took a high resolution model and ran it for the conditions from 35 to 55. Okay, so it's a warmer temperature. And then you have the present day, which is 1979 to 2008. So if you look at the histogram of temperatures from the blue data set, it's like this, right? It's the first histogram. From the high resolution data run for a warmer climate, you have a histogram that looks like this. This is the distribution of temperature samples you will find. Now you will see that supposing you train on only historical data, which is the blue sample, you have not sampled any states that look like this. So because of that, ML will not be able to extrapolate into this space. So what you can do is you can create synthetic data for future climates as well, which is what we try to do. So we try to create a lot of samples for very elevated high levels of CO2, and then use that as training data. And then you will create samples that look like this.
Okay.
So this is what is called the stationarity assumption, which is made a lot. So if you assume that your training data, you often assume that it's stationary, but when the background state itself is non-stationary, then you get error patterns.
Srinivas had a comment that he's already minting money from climate direct carbon capture unit in Texas. They're building a lot apparently. So he enjoyed the talk thoroughly. He will send some money. He will send some money your way.
Okay.
Any other questions?
The check is in the mail.
Yeah. Any other questions I missed out on, guys? Chime in. Don't be shy. All right. If not, I'll thank Balaji again. Fantastic talk. It really is always educational. And we'll have to see you again when you're back stateside to have some more sushi together. So till then, when are you back stateside actually?
November 4th.
Okay. All right. We'll close the call.
Bye, guys.
Fantastic. You don't need incredible. Right?
Hey, thanks, Balaji.
Thank
Okay,
you very
take care,
much.
guys. It's a great pleasure seeing some names from the blasts from the past. Some names I've not heard in many years. So nice to see you all.
Take care.
Yeah, bye.
Only one guy is sending you money, yeah?
And it's in the mail.
Okay, bye.
All right. Thanks, Ab. Take care.
Yeah, thanks, Ab.